Hello and welcome to part 3 of Dev Maths and Stats Refresher Course, Lecture 4, where we move on to matrices. Okay, so in the first part of the lecture, I showed you that vectors help to organise lists of values. So matrices help with tables of values. So for example, you might have a list of prices for different products, which you could use a vector to store. Then you might want to have prices for each year. So you have lots of products and lots of years. So you can put that into rows and columns. So each column has a product and each row has a different year. That gives you a table, and you could write that as a matrix. Notice that in these notes and in most textbooks and articles, matrix names are usually written as capital letters. So let's look at some examples straight away. So there's a matrix I'm calling matrix A. And there's a matrix I'm calling matrix B, matrix C, matrix D, and matrix F. Back into the picture. So just the jargon is that A and B and C are square matrices. E is a 3 by 6 rectangular matrix. 3 times 6 or 3 by 6. First number is the number of rows. Second number is the number of columns. F is a 2 by 2 square matrix. 2 times 2 square matrix. Okay, so that's the basic definitions. Then we can do calculations. They're usually quite straightforward. So here we have matrix C again, and this is multiplying by a scalar, 3 times C. So you should be able to see how you do that, times 3. Here's matrix A, and there's matrix B, and this one is matrix A plus B. So again, you should be able to see how you get from here to here when you add the matrices. So that's multiply by scalar, add to 2 matrices. Here we have divide by a scalar. So there's that rectangular matrix E, and this is E divided by 2. So you should be able to see what happens there. Every single number is divided by 2. So fairly straightforward. Then you can have combinations like this. So this is going to be 2b minus c plus 4a. So you might write this as 2c, I forgot what it was already, minus c plus 4a. So it would appear like that. And that gives you, so you should be able to calculate how you do that. You'd take matrix B, this one, 2 of these, plus, subtract this, and then plus 4 lots of this one. And you should be able to calculate this. So that's all straightforward. And then the final one, matrix B plus matrix E. Oh dear, pink text again. So this is B, this is E. It's not possible to add this plus this. It's not defined, again, because the dimensions are different. So some simple things are not possible. Okay, as with vectors, you have the transpose. So you have B and B dash, or BT, the transpose. And that just looks like that. So every row becomes a column, and every column becomes a row. Okay, so as with vectors, many things are straightforward. Add them, subtract them, multiply by scalar, divide by scalar. It's when you multiply them together, it's a little more difficult. So what I really urge you to do is to practice, make sure you can do these things and the ones on the problem sheet by hand. Before you use Maple or some other fancy computer, you should be able to do it by hand. So there's an explanation in words, which I think is probably best just to go through some answers. So if I'm going to multiply 2 matrices like this, I'm going to do this times this. What you do is first you calculate as though you're doing a dot product. You take, as it explains here, the first row here. So you take this row. Well, I can't hide it. Just the top row, 2, 6, minus 7, and the first column, 5, 1, 5, and take the dot product of those as though they were vectors. So it's 2 times 5 is 10, 6 times 1 is 6, so that's 16, and then subtract 35 gives you negative 19. And the second entry in the top row, you still use the top row here, multiplied by the second column. What's this one? Minus 31. And you keep on going until you get to the very bottom, the last entry in the bottom row, which is this bottom row times this. So negative 3 times 0, 4 times 6, 0 times 9, which gives you 24. The complete answer you get is like this. So you should check that you can do that by hand. Just to give you a break from my poor handwriting, going back to this list, this Wakelet collection of linear algebra visualizations and resources. If you look at that one, this explains the process of multiplying matrices. So you start right at the beginning. To multiply these two matrices, what you do is you take the first row here and the first column, and you take the dots product. So 3 times negative 1 is this, negative 2 times 0, 5 times negative 2. So the blue numbers are coming from here, red numbers are coming from here. You just multiply them together as though it's a dots product, and you find 7. So that 7 goes here, gives you just one number. So you can see there's quite a lot of complex calculation just to get the first number, and then that's the same for the rest of them. So as you move to the next one, okay, it's doing it in that order. So to get the next number down here, you move down, find the 0, but the same 2 times this, this times this, this times this. Then you go to the bottom one, and that gives you the minus 12. So far, to get the first column, we stick with the first column here. Now to get this one, we have to go back to the top row and then move to the second column. So we move to here. So it's 3 times negative 3 and so on to get the 32. Then we go down these rows again to get that one and that one. And then we go to the last one and then down again to finish up here, which is the last entry is that. Okay, so you can access this applet. It'll be on Blackboard and OneNote if we're using that. And you can just press new. I urge you to make sure you can do that, calculate yourself by hand, and then see if it works out with the steps on the calculator. So please do try that out. Right, it's back to the notes. So you should be able to do all of these. So here's some examples. I just stated there's A and B again. So E, as it says here, A dot B is not usually written as dot. That's just the maple command. It's usually just written as AB. So if you're looking at textbook notes or so on, or articles, it'll just be written AB. B dot C would just be written as BC. I really should have made it state C again there, so you have to reference what C is. It's AB and there's BC. This would just appear as A squared, so it's A times A would give you that. Here's a very important one. This is B times A. Okay, now pause the video for a second and think, why is this very important? Thinking back to this one, what do you know? Hopefully you notice that AB is not the same as BA. Now, this is very, very crucial to remember this, because it's a big difference with ordinary numbers. For example, with ordinary numbers, 7 times 8 is the same as 8 times 7. With ordinary numbers, the order does not matter, multiplication is commutative. With matrices, it's not, and the order does matter. When you're following things in textbooks and journals, sometimes, or working on a problem yourself, it's very tempting just to turn the order around, but that completely changes the answer, so you mustn't do it. Don't change the order around because you change everything. Okay, here's f and f squared. Okay, here's e and e times c. Okay, here we have the first error. Hopefully you should be able to think why there's an error, because if I try to multiply e by c, I need to take all of this and match it up with all of this. But it's not possible because here there are 6 numbers and here there are 3. So it's not possible. E squared is also not possible because this does not match with itself. But notice again, when I have found that e times c is impossible, but c times e is possible. Because when this times this is not possible, but this times this is possible because I can multiply. This is 3 here and this is 3 here, so it is possible. So I can calculate this. So what's important is that the number of columns in the first matrix must be the same as the number of rows in the second matrix. They don't have to be exactly the same size. Okay, here's some better news. If I calculate a times b times c, this means calculate b times c first and then multiply by a. This means calculate a times b first and then multiply by c. This is more reassuring because you do get the same answer. In other words, it's what's called associative. So you can change the order of calculation in this way, but you can't change the order in terms of changing the order in which they're multiplied. Another nice piece of news is this one, this comes out to be the same as this, which means that you can factorize and multiply out brackets. So most of the rules of algebra work, factorizing, multiplying out brackets. The order in which you calculate things is fine, but the one which does not work is changing the order of multiplication. It does not work. It's not commutative. So watch out for that mistake. Okay. Finally, in this section, it is possible to multiply matrices and vectors together as long as they fit. So if that's matrix B and that's matrix X, then Bx would give you this vector. So it's almost as though this is treated as a matrix. So 2 times -5, -2 times 5, 3 times -1 is -10, -13, and so on. So you should be able to calculate these as well. Let me just I forgot to repeat what A and Z are. There's A and there's Z and there's AZ. So Fx is F and that's X. Fz, so that's impossible. So that one is impossible because this is 2 here and here you have 3 numbers, so you can't multiply it like that. That's not possible. How about E and W? Will this one be possible? So think to yourself, is that going to be possible? And the answer is yes, it's possible because you have 6 here and 6 here. You only get 3 rows because the number of rows in the answer is 3 because it's every row here gives you a row in the answer. Notice what I've done here. Oops. I have changed it round, so I'm doing now the vector before. So I'm putting the vector down before I do the matrix. So is this possible? No, it's not, because it doesn't make sense to have 5. There's 1 number on this row, too many numbers. That's not possible. That's the transpose of E and Y. So this will be possible. This is the transpose of X. Transpose of X and A. Notice that here I tried to do this. So this times this, XA is not defined because this does not have the same number of the number of rows is 1. Sorry, the number of columns is 1 and the number of rows is 3. That's no good. But if I transpose x first, like this, then it is possible because now I have 3 columns and 3 rows, so that is possible. So I have this. This is a reminder of vector y. This is vector y times dot vector y. So that's a reminder of, in other words, y squared. So that's just the dot product. So 3 times 3 plus 4 times 4 plus negative 1 times negative 1 gives you 26. But what happens here if I transpose y? So I've transposed the first y. When I get the answer to this, what will I get? Will I get a matrix? Will I get a scalar number? How big will the matrix be? Can you visualize how what it will be? The answer is, it's just the same as this, 26. Because 3 times 3, 4 times 4, negative 1 times negative 1. So if I do this and then use the matrix multiplication, it's the same as doing the dot product. You get one single number. However, what if I transpose the second matrix? So I'm calculating this. So the vector times the transpose of the vector. Can you visualize what I will get? Now think to yourself, if I use the rules of multiplying matrices to multiply these ones, will I get a number or a vector or matrix? What will I get? So pause and think, see if you can calculate it. Actually, you get a whole matrix. Were you surprised by that? Well, because using matrix multiplication, I take the 3 times the 3 gives me the 9, then the 4 times the 3 gives me the 12, minus 1 times the 3 gives me the minus 3. Then I do go to the next column here, so 3 times 4 is 12, 4 times 4 is 16, minus 1 times 4 is minus 4, and so on until I get to 1. So y times the transpose of y gives you all the possible combinations of multiplying these numbers. So you'll see that in econometrics as a shorthand for multiplying all the combinations of different numbers together in things like correlation matrices. Okay, so that's the end of the definition of matrices and the basic manipulations that you can do and how you can interact matrices and vectors. So in the next lecture in the next part of the lecture, we go on to look at identities and inverses. But for now, thanks for watching.